Good morning, students. Welcome to your online physics class. And today we are going to start a very interesting topic, a very interesting chapter, that is chapter 13, Magnetic Effect of Electric Current. So, what is magnetic effect of current? What is the meaning of this topic? As the name suggests, magnetic effect produced due to passage of electric current. So when electric current passes through a conductor, it produces magnetic field around it. And this phenomena is called magnetic effect of electric current. This phenomena was discovered by a great scientist, Hans Christian Ørsted. So it's a very interesting story, students. Before the discovery of Sir Christian Ørsted, it was believed that there is no connection between electricity and magnetism. These both are the separate terms. But one day, Sir Ørsted was doing an experiment in the lab. Actually, he was a teacher also, and they were performing the experiment with the students, and the experiment was related with some electricity, some electric wires, battery, and such type of things were placed on the table. And they were passing the current, they were observing the readings as we do in our lab. But there was a compass needle which was lying near to their experimental setup. Suddenly, what Ørsted noticed that when they start passing current to their experimental setup through that conductor or wire, there is a deflection in the needle of the compass needle. So that was a surprising thing for them, that there was no magnet was placed near the compass needle. As we all know, beta, what is compass needle? It is also a kind of magnet. And when we bring this compass needle near a magnet, then it shows deflection. But there was no bar magnet or such kind of magnet placed near the compass needle, but still there was a deflection produced in compass needle. So that was a mystery for Sir Ørsted, that what is happening, why this compass needle is showing this deflection. He again switched off his circuit, and then he repeated the same things, that he switched on his circuit, and again he noticed the deflection. So he repeated this activity again and again, and every time he noticed that when they start passing through the current through the conductor through that wire, there was a deflection produced in compass needle, which was placed near their experimental setup, near their conducting wire. By this incident, Sir Ørsted came to know that there is deflection in compass needle due to magnetic field produced by the passage of current in the conducting wire. So finally he concluded that when current is passing through the conductor, a magnetic field is produced around it. Means it becomes just like a magnet, and it shows the properties which a magnet shows. So after that we find this phenomena. It's an interesting story. Okay, beta. Now you in your earlier classes you discussed about magnet and the properties. So let us recall those properties of the magnet. What is magnet and what is its property? Because in this chapter we are going to use these things. So a magnet is a material or object that produces a magnetic field. or which attract magnetic material like iron, cobalt and nickel. A magnet has an attractive property, that is, it attracts iron, steel, nickel, cobalt, etc. A magnet has a directive property, that is, a freely suspended magnet always shows or always points in north-south direction. Like magnetic poles repel each other, and unlike magnetic poles attract each other. And monopoles do not exist. We already have studied these things, that when we break a magnet and we think that we can separate its north and south pole, but it's not possible. Again, the broken part will develop the another pole, and a single magnet have both poles, north as well as south pole. So we can say that monopole cannot exist. Now, as we say that magnet shows magnetic field. So what is the meaning of magnetic field? Magnetic field can be defined as the space around a magnet in which the force of magnet can be detected. It means, if we are having a bar magnet, suppose, okay, and it attract iron piece or another bar magnet. So have you seen ever that a bar magnet placed at a very large distance and still it can attract? No. It attract the other bar magnet or the magnetic material when we bring it to a particular distance. And if it is far from that, as compared to that distance, there is no attraction. So why it happens? Because that bar magnet or any magnet, it have a region around it in which its influence, its force can be felt, and beyond that there is no force of this magnet and it cannot attract the material. So that region around that magnet is known as magnetic field. Its area, its field where it can work like this. Now, some source of magnetic field. In our daily life, we find some natural magnet, permanent magnet, electromagnet. The earth is also a good having a good magnetic field, and the current carrying conductors. So beta, in today's topic and in this chapter, we are going to study about this type of conductors which can act like magnet in detail. Okay, magnetic field is a vector quantity because it has both direction and magnitude, always remember. And also SI unit of magnetic field is Tesla. It's not given in your NCERT, but you will read it in higher classes. Now, what is magnetic compass needle? You can see in this figure, this is magnetic compass needle and it shows the directions as north, south, east and west. Now you can see this red spot, this shows always north pole. And for distinction, we have colored this portion, and this portion, red portion, shows that it is the north pole of this compass needle. Now, as when we place this compass near a magnetic substance or if near a bar magnet, then its north pole will adjust itself towards the south pole of the bar magnet, and so on. So, needle of magnetic compass is in fact a small bar magnet which is free to rotate in a horizontal plane on a pivot or axis. It can rotate, it can adjust itself according to the magnetic materials. The ends of compass needle point approximately towards north and south directions. The end pointing towards north is called north seeking or north pole, and the other end that points towards south is called south pole. And if no magnetic material is placed near this compass needle, then these needles rest in north and south directions according to the Earth's magnetic field. Now beta, this is activity 13.2 given in your book. This activity is giving us the magnetic field around a bar magnet with iron fillings. If in exam there is question that draw magnetic field lines or show the magnetic field lines with an activity using a bar magnet and iron fillings, then you can write this activity. And in this activity, very simple activity, we will take a we will fix a sheet of white paper on a drawing board using some adhesive material, and then place a bar magnet in the center of it like this. Now sprinkle some iron fillings uniformly around the bar magnet. When we sprinkle these iron fillings, and we'll tap the board gently, just put our finger and press it with our finger, then what we will observe? We'll observe that the iron fillings means iron powder, it arrange themselves in a pattern as shown. What is this pattern called? These are the circular rings. So question arises that when we place iron fillings around bar magnet, then why iron fillings arrange in such pattern? And what does the pattern demonstrate? So the magnet exerts its influence in the region surrounding it, and therefore the iron fillings experience a force, and the force thus exerts makes iron fillings to arrange in a pattern. So this is the reason of this magnetic field of this bar magnet, and according to the direction of magnetic field, these iron fillings, iron powder have arranged themselves. Now this is activity 13.3, another activity given in your book, that is magnetic field around a bar magnet with the help of compass needle. So we can draw these pattern of magnetic field around a bar magnet with the help of compass needle also. If we are not having iron filling, we can use a compass needle, and according to that we can draw. So let us read this activity. That take a small compass and a bar magnet and place the magnet on a sheet of white paper fixed on drawing board using some adhesive material. Mark the boundary of the bar magnet. Now, place the compass near the north pole of the magnet. Like we place this compass here, and now how does it behave? Simply because this is bar magnet and its north pole is at this side, and if we place this compass needle here, then its south pole will point towards the north pole of the bar magnet, and its north pole will point on another side. So it will behave like this, and it will rest in this north-south direction. Wherever the needle points its north pole, we mark a point at that place. After that, again we pick this compass needle from here and we place it on another side in such a way that the south pole of this compass needle will be at this point where we have marked the north pole, and the north pole will go on the other side. And on another side again we'll mark a point with the help of pencil which shows the north pole of compass needle at this position. Again we will do the same activity. We'll pick our compass needle from here and we place at such a place of the compass needle on this paper, so that its south pole will point towards that point and north pole will point on another side. And wherever this north pole will point, we mark another point at that place. Beta, this activity will be more understandable when we perform this activity, and we'll perform this activity. I'll send a video while performing this activity. Then your this activity will be completely clarified. So in this way, when we go on putting the compass needle and putting some points, we get such type of pattern, and at every place we get a dot. When we join this dot, we get these lines. Again we put on another place and we get another line. We repeat this activity by placing it on different positions. So these are the lines which shows the magnetic field, direction of magnetic field around this bar magnet due to this bar magnet. So actually these lines which we get is known as magnetic field lines. Means these are the directions along which the magnetic field of a bar magnet is acting. Now, so we can define now that magnetic field lines, the curved lines along which the iron fillings align themselves, represent the magnetic field lines. According to that activity, 13.2 activity, we can define these magnetic field lines like this. Or another definition of these magnetic field lines can be given as that magnetic field lines is a curve around a magnet such that the tangent at any point on the curve gives the direction of magnetic field at that point. Simply beta, as we discussed, that these lines are telling about the direction of magnetic field. And as we know that if we want to know the direction of a curve, then how we find it? In mathematics we studied that we put a tangent on that curve, and that tangent tell about the direction of that curve. So here this curve is representing magnetic field. So we can define it in such a way also, that tangent at any point on the curve gives the direction of magnetic field. So these are the curves. So these are two definitions. Whatever you find easy, you can learn it for examination point of view. Now beta, let us observe this figure. Again, this is north pole of this bar magnet and this is south pole. And what we are observing, that these magnetic field lines means the direction of this magnetic field is from north to north pole of this magnet to the south pole of the magnet. Means these seems that these lines are emerging from north pole and merging in south pole. Okay, so direction of this magnetic field of this bar magnet is from north to south pole. But now what is happening? This magnetic field lines, these magnetic field lines are going from south to north inside the magnet to complete this curve. It is moving like this. Okay, so what is direction of magnetic field lines inside the magnet? It will be from south to north. Okay, one more thing, what we can another thing we can observe, that these magnetic field lines are far from each other. They are very much separated from one another. But these magnetic field lines, these are very closer to each other. And these magnetic fields are also completing the circle, but we cannot show each and every circle on the paper. That's why we have left it like this. Actually, these are not of this shape. These can be completed like this. These are also in a circular way. Okay. So these are the main points of the magnetic field lines. Let us discuss these. Note, the direction of magnetic field is taken to be the direction in which north pole of the compass needle moves inside it. Therefore, it is taken by convention that field lines emerge from north pole and merge at the south pole. The same thing as we discussed. Now, properties of magnetic field lines. Okay, we discussed some properties in this diagram only, and now we are going to discuss it in detail. So beta, in this figure you can see in A that magnetic field lines of bar magnet, it is showing like this. So it is going from north to south outside the magnet, and this arrow shows the direction of magnetic field lines inside the magnet. It is going from south to north. Okay, if we bring unlike poles together, this is extra knowledge, then the magnetic field lines can be drawn like this, because these are attractive. So these can be shown like this, and this moves from north to south. So always in further topics, whenever we talk about the magnetic field direction, we consider it from north to south. And in this you can see these are the like poles. These magnetic field lines are repelling each other. So this shows such type of pattern. So for examination point of views, let us discuss the properties of magnetic field lines. So magnetic field lines are imaginary lines, but we never have seen such type of lines around a bar magnet. If we are holding a bar magnet in our hand, if we are having iron piece also, so we cannot see these lines pass which are coming from the bar magnet and going towards the iron piece or to the other bar magnet. These are imaginary lines. We are imagining that the line, this magnetic field is acting in these directions. So although magnetic field lines actually do not exist, yet they represent a magnetic field. They are representing the magnetic field, direction of magnetic field, and magnetic field is a real thing. We observe that, we feel that. Second, magnetic field lines are closed curves. As we already discussed, outside the magnet, direction of field lines is from north pole to south, and inside the magnet, the direction of field lines is from south to north pole, and therefore they complete the curve. So these are closed curves. Third, the relative strength of magnetic field is shown by the degree of closeness of the field lines. As we discussed in that figure, that these field lines were very close to each other near the poles of the bar magnet, but they were separated from each other at the other places. So wherever these field lines are closer, it shows stronger magnetic field. The magnetic field is stronger at the poles of the magnet, and it goes and becomes weaker at the center of the bar magnet. When we do the activity with the help of iron fillings, then we will see that the maximum iron fillings have been attracted and pasted on the poles of the bar magnet, and very less at the center of the bar magnet. Very important, no two field lines are found to cross each other. So we have seen closed curves, and each and every line is going to its own path. No two lines are intersecting each other, crossing each other. So this is because it's very important question beta in exam. Question is like this: cross each other and why? And this will be the answer. That this is because if they did so, it would mean that at the point of intersection, the compass needle would point towards two directions, and which is not possible. Like these are two magnetic field lines and these are crossing. Then what will happen? That at this point P, according to this magnetic field lines, this is the tangent which is showing the direction of this magnetic field, and according to this magnetic field line, this is the direction. So it means it is showing that a single this magnetic field line can go in this direction as well as in this direction. It is similar to that way that a person at the same time is found at this place and at this place also. Is it possible? No. That's why we say that the two field lines cannot cross each other. Fifth point, magnetic field lines is a curve around a magnet such that the tangent at any point on the curve gives the direction of magnetic field at that point. So you can easily see, and we discussed a lot about it, that along a curve, if we know the direction, if we want to know the direction, then we put a tangent on any point and we find the direction of the motion of that curve. Okay, now types of magnetic fields. There are two types of magnetic fields: uniform magnetic field, non-uniform magnetic field. So magnitude is equal and direction is same at every point in case of uniform magnetic field, and in non-uniform magnetic field, magnitude is not equal and direction is not same at every point. Uniform magnetic field is represented by equidistant parallel straight field lines, and non-uniform magnetic field represented by non-equidistant field lines, parallel, non-parallel straight field lines. Now you can see in this picture beta, these lines you can see these are equidistant and parallel lines and all have the same directions. So this figure is representing uniform magnetic field, and this exists between parallel poles. Now in another figure you can see this is the bar magnet, and these field lines, these are not parallel with each other. That's why these are showing non-uniform magnetic fields, okay, between the poles of a magnet. This is question. Now activity 13.1, Orsted experiment. Okay, in this experiment what we can do, we will take this XY is a thick wire and we join it with a resistance wire, key and a battery, and then we place a compass needle near it. So let us read. Take a straight thick copper wire and place it between points X and Y in an electric circuit. Place a small compass near to this copper wire. See the position of its needle. Pass the current through the circuit by inserting the key into the plug. So what will happen? We observe that the needle is deflected. When the current is passed through this wire and this needle is placed below this wire, then there is deflection in this compass needle. When current was not passing initially in the wire, then at that time the compass needle was pointing towards north and south direction. But as soon as the current start passing through this wire, this compass needle will get deflected. So why it is deflected? The change in the position of compass needle is due to production of magnetic field in this wire. Current passes, magnetic field produced, and due to the interaction between this magnetic field which is produced around the bar around this wire, current carrying wire, this compass needle also having magnet, it shows deflection. Now in which direction this compass needle will show the deflection? Will it go towards north or south or east or west? How we will come to know? We will use a snow rule. Snow rule is that if current is from south to north, if current is SN, south to north, if current is from south to north, then deflection in the compass needle will be towards west. So let us see with the help of activity 13.4 that again we'll take this wire and we join it with the help of a battery key, means we complete its connections, and we place a compass needle near it or below this wire. Then let us pass this current in this direction. So this direction is from north to south. Now this compass needle will show deflection. In which direction? According to this, if south to north, then west, and if north to south, it will show in east. So this will show deflection in east. Actually, initially it was in this direction. The needle was in north-south direction. But as the current start flowing and it is going from north to south, then it will move towards east. Now again we change the polarity of the battery. Now the direction of current is changed as we change the polarity of battery. Now current is moving from south to north. And now we can easily see the deflection in this needle is towards west. So by this rule we can find that number one thing, that when current passes through the wire, then the compass needle which is placed near that wire or below that wire will show deflection. Secondly, the compass needle will show deflection in which direction, we can also find by this. So this was the introduction of this topic. Finally, in next some classes we are going to discuss about the pattern of magnetic field around a current carrying straight conductor, around a circular loop, and around a solenoid, and some more topics. Thank you, beta.